Okay. In this video, we are going to talk about multi-range ammeters and range changing of ammeters. Okay. Suppose, okay. So before that, let me define a term. So the term is called FSD current of a meter. FSD stands for full scale deflection current. Okay. So by this we mean the current that will cause the pointer to move to the extreme extreme right hand side, extreme position. So that current is called the FSD current. So if I have a meter the current that so the current I that causes this pointer to move to the extreme or maximum value. Okay. So at this position, that current is called the full scale deflection current or FSD current of a meter. Now suppose I have an PMMC meter with FSD current equals say 10 milliampere and say the internal resistance of the coil is also known to be say take it 99 ohm as an example. Okay. So now if I connect this meter and pass 10 milliampere current through this. So if I pass I equals 10 milliampere, then the pointer will come to the extreme right position here. So therefore on this scale I can mark this point as 10 milliampere. This side I can mark as 0 milliampere, 0. Okay. So this is the 10 milliampere marking on this scale. Now suppose I want to measure a current which is say 100 milliampere or which is close to say 1 ampere. Now can I measure that current with this meter? What will happen if I pass 100 milliampere current through this meter? Firstly, the pointer will of course get to its maximum possible position and will get stuck. Okay. So if this is my 10 ampere region, 10 ampere marking, then if I pass 20 ampere current, milliampere current, then also the pointer will come here. If I pass 30 milliampere current, then also the pointer will come here, because the pointer cannot move any further. Okay. Yeah, the meter can also get damaged because of excess current, that is a different issue, but also we cannot measure more than 10 milliampere current directly with this meter. But we can do a small alteration in the this meter, so that we can easily measure 100 milliampere or 1000 milliampere currents with this meter. Any value of current greater than 10 milliampere we can measure. So what is that alteration? So we have to connect a shunt resistance. Okay. So suppose we want to increase the range of this meter, we have to connect a shunt resistance. So we can connect a resistance, okay, in parallel in shunt to this meter. So we can connect a shunt resistance to the meter to increase its range. How? Because if I connect a parallel path to this meter with suitable resistance or conductance, then it is possible that when I pass say 100 milliampere current through this, say if I pass 100 milliampere current, then maybe most of it, maybe 90 milliampere will pass through this parallel branch and only 10 milliampere will pass through the meter, and the 10 milliampere current is good enough for measuring with this meter. So, we can bypass, we can give a parallel route for the excess current to flow through this shunt resistance. Now, what should be the value of this shunt resistance or this parallel resistance? So, if I call this Rs, what should be the value of Rs? Suppose we want to increase the range of measurement to 0 to 100 milliampere. So, with the actual meter we were able to measure only 10 milliampere, okay, because only with 10 milliampere current the pointer goes to the extreme right. But now we want to measure currents between 0 to 100 milliampere, it is a larger range. So, then what should be the value of the shunt resistance? So, basically this means the pointer should go to the extreme right when the current is 100 milliampere, but the pointer goes to the extreme right when this current is 10 milliampere. That means 90 milliampere current must be bypassed through this branch Rs. So, therefore, actually we will have so here the total current will be 100 milliampere, but only 10 milliampere is flowing through the meter and remaining 90 milliampere should flow through this parallel path. Okay. So, 90 milliampere should flow through Rs and 10 milliampere should flow through the meter. Okay. So, now if we know that the internal resistance of this meter is called, this is 99 ohm is given, call it Ra meter resistance or call it Rm, M for meter. So, this is the meter resistance, okay, and this is Rs, and the total current is 100 milliampere. So, we can write that Im, that is this current, meter current, okay, only 10 milliampere. So, this will be given as I, this is I 100 milliampere multiplied by, according to the current divider rule, we can write this is same as Rs divided by Rs plus Rm, and then we know that this is equal to 100 multiplied by Rs plus Rm. This should be 10 milliampere. Okay, so, this side we can write 10 milliampere. Okay. Therefore, now we can write, So milliampere, milliampere cancels. We can write 10 Rs plus Rm. 10 Rs plus Rm should be equal to 100 Rs. Okay. If so, then this 1 0 is cancelled. Now we can write that Rs plus Rm is 10 Rs, or Rm should be 10 Rs minus Rs, which is 9 Rs. Okay. So therefore Rm or Rs should be Rm by 9. Now Rm is given to be 99 ohm, so divided by 9, so this will be 11 ohm. Yeah. So with this value of Rs, we can change the range of this meter to 100 milliampere from 10 milliampere. Now let us take another example. Let us continue this problem. Okay. So what if, so what will be the range of measurement if we choose say Rs equal to 1 ohm. Okay. So now this is my meter, and we know Rm meter resistance is given to be 99 ohm. We are connecting a 1 ohm resistance in parallel. So what will be the range of measurement? Okay. So now the full FSD current is given to be 10 milliampere for this meter. It is given here. Okay. So that means when this current is 10 milliampere, the pointer will reach its maximum position, extreme right side. Okay. And if this current is 10 milliampere, then what is the voltage between these 2 points? Call this A and B. So VAB will be equal to this current 10 milliampere multiplied by Rm meter resistance, which is 10 milliampere multiplied by 99 ohm. So this will be the voltage between these 2 points. So therefore what will be this current? Call this Is, shunt current. Then Is will be VAB voltage divided by Rs, which is known to be 1 ohm. So this we can write 10 milliampere multiplied by 99 ohm. So this is VAB divided by Rs. Rs is given to be 1 ohm. Okay, ohm cancels. So Is becomes 99 into 10, 990 milliampere. So this is the shunt current. Now what is this current? I is nothing but this current 10 milliampere, call it Im, meter current, plus Is, this is the shunt current. So this is Im. Okay. So this will be 10 milliampere plus 990 milliampere is equal to 1000 milliampere or 1 ampere. Okay. So that means when this current is 1 ampere, the meter indicates full scale deflection. That means the meter range is now altered to 1 ampere. So this is the meter range. Okay. So this is how we can change the range of an ammeter. And therefore we can actually, if we have a meter with FSD current 10 milliampere, we can measure any current larger than 10 milliampere by using suitable shunt resistance. Now suppose you all have seen maybe in your lab ammeters which has multiple range, which has say multiple terminals, and depending on the range of current that you want to measure, you connect the wires across the suitable terminals, or it may have some knob with which you can change the range of measurement. How is that done? Basically, so let us talk about multi-range ammeters. Okay. So, what we can do, we can take a meter, say this is a PMMC meter with FSD say equal to, let us take the same value as before, 10 milliampere, and Rm meter resistance or coil resistance equal to 99 ohm. Now, if we connect say a 11 ohm resistance, okay, then as we have seen, when this current is 10 milliampere, that means we have full scale deflection, okay, then this current becomes 100 milliampere. And if we had used a different resistance, so let me disconnect it and let me connect say a different resistance, okay, and say if this is 1 ohm, then when this, so if I connect this like this, then when this is 10 milliampere, this will be 1000 milliampere or 1 ampere. So, this will be then 1 ampere. So, now we can use a switch to change between these resistances. So, what we will do, we will take a switch which you can either connect to this resistance or this resistance, and depending on where you connect, your range of the meter will change. So, if I connect it here, so this is this point, I mark it as 100 milliampere range, and this point, this position is for 1 ampere range. So, this is a multi-range ammeter. Okay. So, we and we can connect more resistances if we need higher ranges. So, if I need say another range of say 10 ampere, what will be the value of this resistance? Okay. So, let me put this as a small exercise for you or homework. Find out the value of this resistance if I want to have a 10 ampere range. Okay. So, this is a multi-range ammeter. Now, we can have another type of circuit for multi-range ammeters, because this circuit has a small problem. What is that problem? The problem is, suppose I am measuring some current which is flowing, which is I and I, okay, and then during the measurement I find that the chosen range is not suitable. Therefore, I am changing the position of this switch. Okay. So, let me draw this here. Okay, so I can change the position of this switch. So I can connect it here or here or here, but you see that when I change the range, say I change the range from here to here, 100 milliampere to 1 ampere, then for a brief moment when the key is moving, when the key is here, this is connected neither to this resistance nor to this resistance. So this path is completely open. So there is no parallel path for a brief moment when I am changing the switch position. So for a brief moment, when we are changing the range switch, okay, no parallel path exists. So therefore this path gets disconnected for a brief moment, and then the entire current should or must flow through the meter, okay, through the meter only, and this current maybe is of a higher value than the FSD current or the allowable current through the meter, and then the meter may get damaged because for a brief moment there is no parallel path. Okay. So the meter may get damaged due to a high current in this brief period of time. Okay. So one solution is this. So the solution is very simple. One solution is this. If I so I will use a different type of switch which is called a make before break switch. So these two are the terminals of the meter through which the unknown current I should enter and leave. Okay. And now see that the switch is so that when it is connected to this, it's okay, but then when I am changing from here to here, this will touch this resistance first before it disconnects from this switch. Okay. So this is a schematic diagram. So basically this is a longer switch, so that this touches the new resistance first before getting disconnected from the previous resistance. So this is called a make before break switch. Okay. So we can say also, so this is like make connection before break connection switch. So this is one solution. So this is one solution. Another solution is called Ayrton shunt. Okay. So let me show another solution, another circuit which is like this. So, if I have my meter with internal resistance Rm, I will connect a set of resistances like this, and then so I have a set of resistances, call them R1, R2, R3. This has resistance Rm, this is the meter, the coil resistance, and I have a switch. This can connect either to this terminal or to this terminal or to this terminal. So, this is a switch, and this is the final inlet and outlet of the meter. So, now say if I connect the switch to position 1, call this position 1, if the switch is here, okay, then the current that enters I will get distributed in two halves. One goes through the meter like this, okay, so it comes like this and goes out. Another half goes through the set of resistances R1, R2 and R3 and then goes out. Okay. So, now we have, so for this position we have Rm and R1 plus 2 plus R3 in parallel. Okay. So, part of the current goes through these three resistances and the part goes through the meter. Okay. Now, this is for position 1. Now, for position 2, so for position 2, if I connect this switch here, I have this Rm and R3 in series. So, part of this current goes through Rm and R3 like this, okay, Rm then R3 like this, and part of the current goes through R1 and R2 and then out. Okay. Then, so for position 2, I have Rm and Rm plus R3 and R1 plus R2 in parallel. Okay, this is for position 2, and for position 3, so if I connect this switch here, then I have Rm, R3 and R2 in one path and R1 in the other path. Okay. So, I have Rm plus R3 plus R2, this is one path, and R1 alone. So, these two are the two paths. Okay. So, let me also write for position 1. So, for position 1 we have Rm alone and 1, 2, 3 together. So, these two are the two parts. Okay. So, you see that if I connect this meter to position 3, then the shunt path or the path parallel to the meter is of a lower resistance value compared, and this the other path, meter path, has Rm plus R2 plus R3. So if I connect it here, more current is bypassed. Okay, so for position 3, more current is bypassed from the meter. So this is a higher range. So position 3 is higher range, and position 1, if I put this switch here, then the shunt resistance is now higher, R1 plus 2 plus 3 compared to Rm, which is alone. Okay, so this, for this position, more current goes through Rm, comparatively less current goes through the parallel path. So this will be a lower range. So this is the lower range. Now, so this is another arrangement, and observe that when I change the position of the switch, okay, then even if the switch is, say, somewhere in between, it is not connected to either of the terminals, no problem. I mean, no problem from the perspective of the meter, because then this circuit is completely open. There is no path for this current to flow at all. So the meter can never get excess current, unlike this situation where if the switch is here, it is not touching any of the parallel paths, then all the excess current will flow through the meter. In this case, the circuit is broken completely. So the current I will stop when the switch is here between two terminals, and therefore excess current will not flow through the meter. So from the perspective of the meter is more safe. Okay, so this is called Ayrton shunt, and so this is another arrangement one can have, and one can compute the values of these resistances depending on the required ranges. So we will take a problem in a tutorial class where we will calculate the values of these ranges, of this values of these resistances to get suitable ranges. Okay, thank you.